This paper talks about using machine learning for antibody CDR design, and their workflow shows here. First, they have the library contains CDR sequences, and then they generate their enrichment assay as training data for the machine learning algorithm to generate the new sequences. Meanwhile, they have their control sequences and the sequences in their library, and they generate the enrichment assay again, and then they perform a characterization to evaluate the models. They use the log 10 of round-to-round ratio of sequence frequency as enrichment to indicate the antibody specificity. So if its value is positive, then it's enriched. If it's negative, then it's not enriched. Here it shows the overview of their n-squared sequence optimization methodology. So first part is training. They have their NGS data. They train their ensemble models, and once the model is trained, they fixed their model parameters, and then they use a seed sequence as input and use those parameters to generate a new sequence. So again, here shows how they generate a new sequence. They have a seed sequence in one-hot representation. They run the gradient ascent optimization by using the model parameters. In this way, they relax their one-hot representation, which means their number is not just constrained in 0 and 1s, and they're allowed to be any other value in order to get the gradient descent, the best result. After the k iteration, they add they perform argmax to convert the maximum value to 1 and the rest of the value to 0, and that's how they generate their new sequence. This paper also talks about the 3 ways of using machine learning algorithm. The first is to predict the panning enrichment. So as we can see here, the experimental enrichment and the predicted enrichment, their Pearson R is relatively close. And they also show a high area under the curve for AU-ROC using the convolutional neural network. This paper also compared the single net and the ensemble net. By using ensemble method, they generate a high Pearson R, high R square, and also a low mean square error. And the second way is to using ML to eliminate the non-specific antibodies that bind to undesired target. Here shows how they define the specific and non-specific binders by using positive and negative enrichment. So in this paper specifically, they're trying to eliminate the anti-B antibody that also binds to ENT. So using the phage display panning, 3 rounds of them, the data, they can generate a model that predicts a sequence that binds to ENT. And meanwhile, they have the sequence of anti-B antibody, and then they can remove those sequence that binds to ENT. So the model shows a pretty good results. Again, they have eliminated majority of the non-specific binders, and meanwhile they remain their specific binders. And the last way is showed how their machine learning design sequence, their enrichment, how it is. So by using their n-squared, they have shown a positive distribution shift for the enrichment of the design sequence. They also showed the enrichment of sequence after their machine learning models. They only showed n-squared because all the other methods, their enrichment are lower the value here, so they're not shown here, which means, again, they showed their machine learning design sequence has a good specificity.